Look around you. A snowflake falls with perfect six-fold symmetry. Crystals grow in precise geometric patterns. Flowers bloom with mathematical regularity. Your face has left-right symmetry. Even at the atomic level, electron orbitals arrange themselves in perfectly ordered shells. The universe displays an obsession with order that borders on the supernatural. But here's what should really make you wonder. This isn't just aesthetic preference. This perfect mathematical order is actually the foundation of every physical law you've ever heard of. Conservation of energy, conservation of momentum, conservation of electric charge. Every single conservation law in physics emerges from a deeper principle, so elegant, it seems too good to be true. By the end of this, you'll understand why symmetry isn't just a pretty pattern, but the organizing principle behind all of reality. You'll see how mathematical beauty literally creates the laws of physics, how the same pattern that makes snowflakes hexagonal also determines why energy can neither be created nor destroyed, and most remarkably, how this insight led to a complete reorganization of our understanding of matter itself. The story begins with a question that sounds almost mystical. Why does the universe seem to care so much about mathematical beauty? Why do the fundamental laws of physics possess such elegant symmetries? Why does nature appear to be written in the language of mathematics? The answer turns out to be even more profound than the question. The universe doesn't just happen to be mathematical. It is mathematical. And what we call physical laws are actually mathematical inevitabilities arising from the requirement that reality be consistent with itself. This insight revolutionized physics, but it started with something much simpler. The observation that nature seems to treat equivalent situations equivalently. If you perform an experiment in London and then perform the exact same experiment in Tokyo, you get the same results. If you do an experiment today and repeat it tomorrow, the laws of physics haven't changed. Rotate your laboratory, and the laws of physics don't care about your new orientation. These seem like obvious statements, but they're actually profound constraints on what kind of universe is possible. The fact that physics doesn't depend on where you are in space means that space itself has a certain symmetry. The fact that physics doesn't depend on when you perform an experiment means that time has a symmetry. The fact that physics doesn't depend on how you orient your laboratory means that space has rotational symmetry. Now comes the stunning revelation that changed everything. Each of these symmetries, spatial translation, time translation, rotational symmetry, doesn't just describe how the universe looks. Each symmetry actually creates a conservation law. The symmetry of space under translation generates conservation of momentum. The symmetry of time under translation generates conservation of energy. The symmetry of space under rotation generates conservation of angular momentum. This connection between symmetry and conservation was discovered by a remarkable mathematician named Noether, and it's arguably the most beautiful theorem in all of physics. Noether's theorem shows that every symmetry in the laws of physics automatically creates a corresponding conservation law. Symmetry doesn't just describe conservation, it creates conservation. Think about what this means. The reason energy is conserved isn't because someone decided to make it a law. Energy is conserved because the universe has temporal symmetry, because the laws of physics are the same today as they were yesterday and will be tomorrow. Conservation of energy is a mathematical consequence of time's uniformity. This completely reverses our understanding of how physics works. We used to think that conservation laws were fundamental principles that we discovered through experiment. Now we understand that conservation laws are inevitable consequences of the symmetries that space and time must have for reality to be mathematically consistent. But the power of symmetry thinking goes far beyond these basic conservation laws. In the 1960s, this approach led to the most dramatic reorganization of particle physics since the discovery of the electron. The key insight was to look for symmetries not just in space-time, but in the abstract mathematical spaces that describe particle properties. Consider the overwhelming chaos of particle physics in the 1950s. Hundreds of different particles had been discovered in cosmic rays and particle accelerators. Protons, neutrons, pions, kaons, lambda particles, sigma particles, xi particles, and seemingly endless zoo of exotic entities with no apparent organization or underlying logic. It was like having hundreds of chemical elements with no periodic table. Each new particle discovery added to the confusion rather than clarifying the picture. Some physicists began to wonder if there was any underlying order at all, or if nature, at its smallest scales, was simply irreducibly complex. The breakthrough came from recognizing that this apparent chaos actually contained hidden patterns, symmetry patterns that became visible only when you organized particles not by their mass or lifetime, but by their fundamental properties like electric charge, spin, and response to different forces. When particles were arranged according to these more abstract properties, something remarkable emerged. They organized themselves into elegant geometric patterns called multiplets. 8 particles here, 10 particles there, 27 particles over there, all arranged in symmetric patterns that looked like mathematical objects called group representations. This wasn't just interesting mathematics, it was a revelation about the fundamental structure of reality. The pattern suggested that what appeared to be hundreds of different elementary particles were actually different manifestations of a smaller number of truly fundamental entities, combined according to precise mathematical rules. This led to what became known as the Eightfold Way, a classification scheme that organized all known particles into a small number of symmetric families. Just as the periodic table revealed that all chemical elements could be understood in terms of a smaller number of basic building blocks, the Eightfold Way revealed that all particles could be understood as combinations of an even smaller set of fundamental constituents. But the Eightfold Way did more than just organize existing knowledge. It made testable predictions. If the symmetry pattern was real, then certain multiplets were incomplete. They were missing particles that ought to exist to complete the symmetric pattern. The theory predicted the existence of new particles with specific properties, and when experimenters went looking for them, they found exactly what the symmetry had predicted. This was symmetry thinking at its most powerful. Mathematical patterns weren't just describing what we observed, they were predicting what we ought to observe but hadn't yet discovered. The universe's commitment to mathematical beauty was so strong that it demanded the existence of particles purely to complete symmetric patterns. The success of this approach led to an even more radical insight. If symmetric patterns were so fundamental to particle physics, perhaps the particles themselves weren't fundamental. Perhaps what we called particles were actually composite objects made of truly elementary constituents that combined according to the rules of group theory and symmetry. This insight led to the quark model, which explained all these symmetric particle patterns by proposing that hadrons, particles that feel the strong force, are made of combinations of just a few types of fundamental constituents called quarks. 3 quarks combine to make baryons like protons and neutrons. A quark and an antiquark combine to make mesons like pions and kaons. The quark model wasn't just a mathematical convenience. It was a deep statement about how symmetry principles constrain the structure of matter. The specific symmetries observed in particle physics experiments dictated exactly how many types of quarks there could be, what properties they must have, and how they could combine with each other. But symmetry thinking revealed something even more profound. Not all symmetries are perfect. Some symmetries are broken. They're almost perfect, but not quite. And these broken symmetries turned out to be just as important as perfect ones, because they explained why the universe has the rich structure we observe rather than being completely uniform and featureless. Perfect symmetry would lead to a perfectly symmetric universe. No variation, no complexity, no interesting phenomena. Broken symmetry creates the possibility for interesting physics. When a symmetry breaks, it usually breaks in a very specific way that preserves some symmetries while destroying others, creating patterns of complexity that follow precise mathematical rules. For example, the electromagnetic and weak forces appear to be completely different at low energies, but at high energies they merge into a single electroweak force with a larger symmetry. The breaking of this electroweak symmetry as the universe cooled created the distinction between electromagnetism and the weak force, while also generating the masses of particles like the W and Z bosons. This process of spontaneous symmetry breaking is beautifully illustrated by what's known as the Higgs mechanism. Imagine a perfectly symmetric landscape, a flat plane extending in all directions with no preferred orientation. A ball placed at the center sits in perfect equilibrium, and the situation has complete rotational symmetry. Now imagine that the flat plane is actually the top of a hill, and the ball naturally rolls down to the bottom. But instead of rolling into a simple valley, it rolls into a circular valley, like the indentation around the bottom of a wine bottle. The valley itself preserves the rotational symmetry, but the ball must come to rest at some particular point in the valley. When the ball settles at any specific point in the circular valley, it breaks the rotational symmetry. The physics now has a preferred direction, the direction from the center to where the ball sits. Yet the underlying equations still possess the original symmetry. The asymmetry emerged spontaneously from a completely symmetric starting point. This is exactly what happened with the Higgs field in the early universe. At extremely high energies, the Higgs field was symmetric and particles were massless. But as the universe cooled, the Higgs field underwent a phase transition, settling into a new configuration that broke the symmetry. This symmetry breaking didn't eliminate the underlying mathematical structure, it revealed hidden aspects of it. The remarkable consequence is that particles interacting with the Higgs field in its symmetry-broken state acquire mass, while particles that don't interact with it remain massless. The photon doesn't interact with the Higgs field and stays massless, allowing electromagnetic radiation to travel at the speed of light. The W and Z bosons interact strongly with the Higgs field and become very massive, which is why the weak force is so short-ranged. What makes this particularly elegant is that the masses aren't arbitrary. They're determined by the precise way the symmetry breaks and the strength of each particle's interaction with the symmetry-breaking field. Mass emerges as a secondary consequence of more fundamental symmetry principles. The mathematics underlying these symmetry arguments involves sophisticated group theory, the branch of mathematics that studies symmetrical structures. Different types of symmetries correspond to different mathematical groups, and the properties of these groups constrain what kinds of physics are possible. For instance, the group SU3, the special unitary group in 3 dimensions, governs the color symmetry of the strong force and determines how quarks can combine to form particles. The group SU2 governs the weak isospin symmetry that relates particles like electrons and neutrinos. The group U1 governs electromagnetic charge conservation. These aren't arbitrary mathematical abstractions. These groups represent the actual symmetry structure of physical reality. When we say a theory has SU3 symmetry, we're making a precise statement about what transformations leave the physics unchanged. When we say this symmetry is broken down to SU22XU1, we're describing exactly how the mathematical structure reorganizes itself. The elegance of this approach is that complex physics phenomena become inevitable consequences of simple symmetry principles. You don't have to postulate dozens of different forces and particles and hope they work together correctly. You identify the relevant symmetries, understand how they can be broken, and the forces and particles emerge automatically from the mathematical structure. The mathematics of symmetry and symmetry breaking has become so central to modern physics that it's hard to imagine the field without it. Gauge theories, supersymmetry, string theory, theories of quantum gravity, all are built around sophisticated uses of symmetry principles that extend the insights of the eightfold way to ever more fundamental levels. What emerges from this is a picture of reality, where mathematical structure isn't something imposed on the universe from outside. Mathematical structure is the universe. What we call matter and energy are stable patterns in mathematical spaces whose geometry is constrained by symmetry requirements. This suggests something profound about the relationship between mathematics and physics. We often wonder why mathematics is so effective at describing the natural world. The answer suggested by symmetry thinking is that mathematics doesn't describe the natural world. Mathematics is the natural world. Physical reality is mathematical reality, experienced from the inside. When you look at a snowflake's perfect hexagonal symmetry, you're not seeing an accidental arrangement of water molecules. You're seeing a direct manifestation of the mathematical constraints that govern how molecules can arrange themselves in energetically favorable configurations. The symmetry isn't added to the physics. The symmetry is the physics. When you observe conservation of energy in any physical process, you're witnessing the mathematical consequences of temporal symmetry. The conservation law isn't something separate from the symmetry. It is the symmetry, expressed in the language of energy and dynamics. This perspective transforms our understanding of what it means to do science. Instead of thinking of ourselves as discovering pre-existing laws of nature, we might be better understood as exploring the mathematical structures that are logically possible, and finding that only a very small subset of those structures can be self-consistently realized as physical reality. The search for symmetries becomes a search for the fundamental logical constraints that any possible universe must satisfy. The discovery of new symmetries becomes the discovery of new mathematical truths about the structure of reality itself. But perhaps most remarkably, this approach suggests that the apparent complexity and chaos of the physical world might be much simpler than it appears. If all the diverse phenomena we observe are expressions of underlying mathematical symmetries and symmetry-breaking patterns, then understanding those patterns gives us a kind of unified perspective on all of nature. This is why the study of symmetry has become so central to fundamental physics. It's not just one tool among many for understanding nature. It's the key to understanding why nature is understandable at all. The mathematical patterns that govern particle interactions, the conservation laws that constrain all physical processes, the organizational principles that create complexity from simplicity. all emerge from the universe's deep commitment to mathematical consistency and beauty. The next time you see any regular pattern in nature, the spiral of a shell, the branching of a tree, the orbital structure of atoms, the crystalline arrangement of minerals, remember that you're looking at the direct expression of mathematical symmetries. These aren't coincidences or approximations. They're exact manifestations of the geometric constraints that make reality mathematically possible. Every equation in physics, every conservation law, every organizational principle in chemistry and biology, all are reflections of deeper symmetries in the mathematical structure of reality itself. The universe doesn't just happen to be beautiful. The universe is beautiful because beauty, in the form of mathematical symmetry, is what makes existence possible in the first place. And you, as a conscious observer capable of recognizing these patterns, are not separate from this mathematical structure. Your ability to appreciate symmetry, to find beauty in mathematical relationships, to understand the logical constraints that govern physical reality. These capabilities suggest that consciousness itself might be the universe's way of appreciating its own mathematical elegance. In recognizing the perfect order that underlies everything, you're participating in the universe's ongoing project of understanding itself through the very mathematical principles that make its existence possible.